Time to move on to our hypothesis testing about claims on the mean. This is going to be the last section that we cover in Chapter 8. The sections on standard deviation and variance we're not going to cover. We might look a little bit at Excel, but we're not going to do the resampling techniques that are given there. So our key concept here, excuse me, is we're going to test a claim about a population mean. And it's one of the most important methods, most commonly used methods that's presented in this course. It deals with a very realistic sense of testing what a population mean is, or a claim about a mean. And we're going to stress the situation where the population standard deviation is not known, because that's the most common. If we don't know the population mean, chances are we do not know the population standard deviation. We will take a quick look at the end of this presentation of what changes if we do know the population standard deviation. So our objective is to do that formal hypothesis test about a mean. Our notation, n is our sample size. X bar, remember, is the mean of a sample. S is the standard deviation of a sample. Now, if it were a population, sigma is a population standard deviation. Many textbooks spend a lot of time talking about how to do a test if you have that population standard deviation before going over to what do you do if you don't. Well, in practice, 99% of the time you don't have it, so that's why we're going to look at just using the sample standard deviation. And then mu of x bar is the population mean. That's actually, mu of x bar is actually the mean of the sample means. Just mu itself is the population mean. A little bit of a typo on the part of the PowerPoint there. So our requirements, of course, it has to be a random sample from the desired population. And then this next one is really the important one. Either the population has to be normally distributed, or we must have a sample size of greater than 30. So if our sample size is bigger than 30, we don't have to worry about the distribution of the population. If the sample size is smaller than 30, then we have to do either a box plot or a histogram or something to estimate to see if the population is approximately normally distributed. Our test statistic is going to be our sample mean, so that's from our data sample that we take, minus the mean from the null hypothesis over the sample standard deviation divided by the square root of n. So we can use Excel to find critical values for the student t-distribution, to find p-values for the student t-distribution. I'm also going to show you how to use StatCrunch for some of that as well. So requirement of normality. So if the sample size is greater than 30, like we said, we don't have to worry about it. But if the sample size is less than 30, if it's between 15 and 30, we just have to make sure it's close to normally distributed. So we can just use a box plot or a histogram and see if it's approximately bell-shaped and go from there. If it's much smaller than that, then we need to make sure that the data is really, the population really is normally distributed. We can't just estimate it using a plot like that. In this text, we're going to assume that in most cases, even if the sample size is less than 30, we're going to assume the population is normally distributed. We will show a little bit about checking that, but not a whole lot of time is going to be spent on that. So recall important properties of our student t-distribution. So the student t-distribution changes for different sample sizes. It is, however, still a bell-shaped curve like the normal distribution. The difference is, while the mean of the t-distribution is still 0, just like the standard normal distribution, the standard deviation of the t-distribution is not 1. It's always going to be bigger than 1. The smaller the sample size is, the bigger that standard deviation is. The bigger the sample size is, the smaller it gets until it reaches 1. So if you have a big enough sample size, the t-distribution is essentially just the normal distribution. So we're going to take a look at an example here of adult sleep times. So we obtained sleep times here for several adults. It looks like 12 adults. So sample size, n equals 12. We found the mean. The mean of that sample is 6.38333333 hours. Standard deviation, 1.924094 hours. So a common recommendation is that people get at least 7 to 9 hours of sleep a night. We're going to do the p-value method with alpha of 0.05 level of significance to see what we come up with here. So the sample is a simple random sample. That was given in the problem. Second requirement, the sample is not bigger than 30. So the sample size of 12, we have to be relatively sure that this is close to normally distributed. So I would just look at the histogram here. If you look at drawing through the histogram, it is approximately bell curved. It is slightly skewed, but not a lot, so we're okay. We didn't really do normal quantile plot in this course, but that's a normal quantile plot that shows that those dots are pretty close to a straight line. We're close enough to normally distributed to make sure that we can go ahead with this test. So let's look at our solution. So the first, we have to make the claim the mean of the adult sleep is less than 7 hours. So that becomes that mu is less than 7. The alternative to this, the opposite side of this would be greater than or equal to 7. Now remember, the one that contains the equal to becomes the null hypothesis. So the null hypothesis is going to be that the mean is greater than or equal to 7. Remember, we just write it as equal to, and the alternative is going to be that the mean is less than 7, which is our original claim, and we're trying to gather evidence in favor of our original claim, or to reject the opposite of our original claim. So, as specified in the problem, we're dealing with alpha of 0.05 level of significance. And because the claim is made on a population mean, the sample mean is going to be an unbiased estimator of that. So we can do a test for the sample mean, on the sample mean. So our sample mean was 6.8333. We're going to subtract. Remember that 7 comes from the null hypothesis. Then we take our standard deviation, 1.9244, or 240,984, divided by the square root of the sample size. Remember, 12 is the sample size. That comes out to give us a test statistic of negative 0.290. So, what does that tell us? Well, first, let's look at what the Excel stat output would be. This would be our Excel stat output. This is our test statistic that we just calculated, the negative 0.290. And Excel stat is giving us a p-value of 0.389. So a p-value of 0.389 is not less than alpha of 0.05. So that means we would fail to reject our null hypothesis. So because this p-value of 0.389 is greater than the level of significance of 0.05, we do fail to reject, which means we do not have enough evidence to reject the idea that people get at least 7 hours of sleep a night on average. Basically, we're saying even though our sample mean was less than 7, we're saying that it's not far enough down that we can rule out the fact that we just happen to randomly select people that get little less hours of sleep in a night. Now, let's review some of this. First of all, the test stat. We calculated the test stat without technology. We had that negative 0.29. If I wanted to find the p-value for that, the alternative is less than, so we're finding the probability that t is less than negative 0.29. And this is for 11 degrees of freedom. Now remember, our sample size is 12, so degrees of freedom is 11. So we're looking at t inverse right here. We're going to put in a negative 0. Not t inverse, we're looking at just t distribution, sorry. T distribution right there. negative 0.29 with 11 degrees of freedom. And, oops, what am I missing? Oh, got to say cumulative. So there we get the 0.389, the same as we got with the Excel stat output. Let's go to StatCrunch here in MyMathLab. And I think StatCrunch is a much neater, cleaner way of doing this calculation. So if we get to StatCrunch, we're going to go to Stats, and we're going to go to T-Stats, one sample, with summary. Remember, we don't have all the data points from our sample. We just have the summary statistics. So the sample mean was the 6.8333333. Sample standard deviation, let's see, I pull that up here. 1.924. I'm just going to write in 1.924. That should be close enough. Sample size is 12. Our hypothesis test. So this is going to be 7, and this is less than. I'm gonna put down here to show the critical value just to show it. If I hit compute, there's my sample mean, standard error, degrees of freedom. My test stat is a little off because I rounded my degrees of freedom, my standard deviation. Critical value would be a negative 1.796, p-value 3.85, which is about what we had. So you can see we get the same output here. Let's go back. I'm going to redo this one, and I'll put in the exact standard deviation, see if that makes much of a difference. So sample mean. Let's get my standard deviation, 1.9240984. 1.924. 0894. 0984. Good thing I double checked that. And our sample size, again, is still 12. This is 7 and less than. Everything appears to be in there correctly now. Let's hit that and see if we get closer to the exact. So it's still giving us a little bit off on our stat, again, because putting this in is not going to be exact. I might not have got the exact number of 3s in there. But we see everything comes up really close to what we had with our calculations. Now, I did not click critical value that time to show the critical value, but we saw that critical value 1.79. How would we get that? Well, if I have, oops, this is not what I want. My test, my bell curve, because even the t-stat, the t-distribution is still bell curve. And my alternative hypothesis is less than, and we're looking at 0.05. So this cutoff is going to have an area to the left of 0.05. So in Excel, I can do an inverse t. So t inverse of 0.05 for 11 degrees of freedom. And I get negative 1.796. So that would be saying as our rejection here rule would be, we would reject the null hypothesis if the test statistic is, now since it's, the alternative is less than, we have to be less than negative 1.796. So just looking at our test statistic of a negative 0.290, we definitely are not nearly small enough to reject that null hypothesis. So finding it without technology, we have that table A3. I actually haven't been able to find in the homework anywhere in MyMathLab where that table is linked. So I'm assuming we don't need it. I can show you here, though, what the table looks like, so that if you do run across it, you can look at it. Let's see here. Oh, that's not what I want. I want this one. So here's a student T. Here's a copy of the student T distribution, very similar to what the book does. So you can see along the left side is degrees of freedom. So we would have 11 degrees of freedom here. So we'd be looking at this row. And now usually on top it says both two-tail and one-tail areas. Here we just have in a single tail area. And our single tail is going to be 0.05. So we're looking at that column. So we follow that down, we get this number right here, 1.796, which is what we were finding with technology. Now the alternative is less than, so we're going to use a negative 1.796 as our critical value. But that's how the table works, is just like that. So we can get that same value of 1.796, or we can take our test statistic of negative 0.290. Now we're going to just use a positive because that's what the table shows, and see if we can find anything close to that in our table. So 0.290, well, the smallest our table goes is 0.87. So what this is telling us is that our p-value is at least 0.2. Now I believe the one in the book doesn't go up to 0.2, it just goes up to 0.1. So our test statistic is smaller than 1.36. So we know the p-value is at least 0.10, which is all we really need to know. The p-value is not smaller than the level of significance of alpha of 0.05. So we know we failed to reject. So using the table, we cannot get an exact p-value. We can just say that the p-value is less than 0.10. Or, sorry, not less than, is greater than 0.10. Therefore, we get that same conclusion of we cannot reject. And so here's just reviewing the critical value method. We would find that critical value using 11 degrees of freedom, just 12 minus 1. And we either use the table that we just saw, or we can use Excel, getting us the critical value of the test statistics, that negative 1.796. It's negative because the alternative hypothesis is less than. And of course, because our test statistic is not less than that, we fail to reject. So basically, we don't have enough evidence to prove that people get less than 7 hours of sleep a night on average. So now then there's the confidence interval method, which when we did proportions, we said the confidence interval method wasn't exact. For means, the confidence interval method is exact. So when we're looking at this, we have 0.05 is our level of significance in a single tail. Remember, a confidence interval is always two-tailed, so we have to make it symmetrical. There's 0.05 on the other tail, which means there's 90% between here, 0.90 or 90% in the middle. So we're looking at a 90% confidence interval for this. We construct that 90% confidence interval, and I'm going to just go ahead and go to Excel stat and do it there. T-stat, one sample with summary. And we again have 6.8333333. This was 1 point. Scroll back up to get my standard deviation. We're going to do 1.9924 again. So 1.9924. Sample size of 12. And we're doing a confidence interval of 90%. And we're going to show it. And so our interval goes from 5.800 to 7.866. So what we had here, 5.800 to 7.866, 7.87 is our confidence interval. So we're saying we're 90% confident that the average hours of sleep that a person gets in a night is between those numbers. Now, again, if we're looking at a range, 5.8 to 7.87. 7 hours is in that range. And this range contains values that are above 7, which means we cannot rule out the possibility that the true mean is greater than 7. Remember that confidence interval, there's an equal chance of the true population mean being at any point along that interval. So because the interval contains points that are greater than the 7, we cannot reject that idea of the mean being greater than 7. So a second example here, let's look at the example here of our mean body temperature is not really 98.6 degrees. So we, appendix in the book, again, you don't have a hard copy of the book, but the data, temperatures taken, the time of day usually does make a difference. So the data was taken at 12 a.m., so midnight, 106 people. So sample size, n equals 106. The sample mean is 98.2 and a sample standard deviation of 0.62. So we're going to use a level of significance of alpha of 0.05 to test the common belief that the mean is 98.6. So let's check our requirements. This is a simple random sample. Sample size is greater than 30, so we don't care if the population is normally distributed or not. So our claim is that this temperature is 98.6. So that's equals 98.6. So the opposite of that would be not equal to 98.6. So that means our null hypothesis has to be the one that contains the equal, which is, so the mean is equal to 98.6. The alternative would be not equal. So this is going to be a two-tailed test. So what that means is not equal to means we could reject if we get a sample value is too small or too large. So as stated in the problem, our significance level is 0.05. And again, since this is a test for a population mean, the sample mean is an adequate descriptor of it. So then here we're looking at calculating our test statistics. So our sample mean of 98.2. minus our hypothesized value and the null hypothesis of 98.6. And then our standard deviation of 0.62 divided by the square root of our sample size of 106 gives us a test statistic of a negative 6.64. Now that's pretty far from zero. Almost always going to reject on that. So let's find some critical values here. Since this is a two-tailed test, that alpha of 0.05 gets split between the tails. So this is a 0.025 on this tail, 0.025 on this tail. So we can use either one of them to get our critical value. I'm going to use the 0.025. So if I go into Excel and I use T inverse of 0.025, sample size is 106, so my degrees of freedom are 105. I get a negative 1.983 critical value. So T critical is negative 1.983. Well, this is definitely less than that, which means we're going to reject the null hypothesis. Now let's find the p-value here using technology. So in Excel, our p-value equals T distribution. Now we're going to do the T distribution two-tail here. And I'm going to put in negative 6.64 with 105 degrees of freedom. And I get, oops, looks like it's going to be too small. I expand it out. Oh. Let's see, let me make that. So we get almost zero. That E negative 9, that's, by the way, so what went wrong there, by the way, is when you use the two-tail, you always have to put in the test statistic as positive. So I just changed it to a positive 6.64 and it worked. That E negative 9 means times 10 to the negative 9. So this is literally 0.0000001419. So basically 0 is our p-value there. And this is showing that t-distribution here, getting that basically that 0 p-value. So this is the t-distribution to get our p-value. Our critical values, as we saw, was 1.983. We can get those off the table as well if we wanted to. So one tail, this is two tails. So one tail, we want the 0.025. So we want this one. So we're going to look at that column there. Oops. Now run that all the way down to the bottom. Now this only goes up to 17. Now there would be more lines to this, but at 17, you can see I'm down to 2.1098. We would have to get a second page, which I didn't copy here. So, but 105 is probably not going to be on the t-table. There's probably going to go from like, this is probably going to go up to like 30, then jump to like 40, 50, maybe another number in between there, but then like 100 and 200. So we would probably just use the 100 to get what we would need there. Their 105 probably is not going to appear on that table. So we wouldn't be able to get an exact critical value off of that. Let's run this in XLStat. Or not XLStat, in StatCrunch. So we'll close this down and we're going to go here's T-stats, one sample with summary. Let me get my information out of here. So I have a mean of 98.2 and a standard deviation of 0.62. 98.2, standard deviation of 0.62. My sample size of 106. Now this was equal to 98.6. This is not equal to, so we're good there. Now I'm going to show critical value. I'm going to click that so I show my critical value, level of significance of 0.05. I hit compute. So there's my critical value, 1.983, just like I found. P-value is less than 0.0001, so it's really small. There's the test statistic we found, negative 6.64. It's all right there. Like I said, I think StatCrunch, since it's available, it's right in my math lab for this course, probably the simplest way to go about doing these. So, again, p-value is less than alpha, so we reject. Our test statistic is less than our critical value, so we would reject. Let's look at the confidence interval method. So the confidence interval, we get the confidence interval would be from 98.08 to 98.32. If I look at that on a number line, 98.08 to 98.32, well, 98.6 is up here somewhere. So there are no points in that interval that are on the other side of 98.6. 98.6 is not in the interval. So we're saying that at 95% confidence, since this is two-tailed test, at 95% confidence, we're that sure that 98.6 is not in the interval. It's not the true value. So the confidence interval confirms us rejecting that null hypothesis. So there is sufficient evidence to reject the claim that the common belief is true, to reject that the population mean for body temperature is 98.6. This is a test that's actually been done, and we have shown that over the years, average human body temperature has dropped slightly. So what if we do actually know the population standard deviation? That's this value right here, sigma. Well, as long as we have a simple random sample, and we either have a sample bigger than 30 or the sample, the population is normally distributed, so we still need to meet those requirements. But now we can just use the normal distribution for all this. Well, the normal distribution, it's a lot easier to calculate. We can just use Excel to do the normal calculations like we've seen. And the test statistic is going to be a z statistic instead of a t statistic, but everything else is the same. You can see it is the sample mean minus the population, or the mean stated in the null hypothesis, over, now it's going to be the population standard deviation divided by the square root of the sample size, but it's going to give us the same amount. The only difference is doing the p-value, you're going to use a normal probability, or to find the critical value, you're going to use an inverse normal for finding those. So that's the absolute only difference. Like I said, in reality, in practice, you almost never actually know the population standard deviation. So that's why we're only showing just like a brief little thing of this here. But the process is still exactly the same. You're just going to use the z table or the normal table instead of the t table. So that is hypothesis tests for population means. That is all we have for this week. Have a great week.